The universe, when observed from a distance, appears calm. On the night sky, it seems almost still, a black canvas filled with scattered points of light that do not change in any visible way within a human lifetime. For most of human history, this appearance shaped our understanding of the cosmos. The stars were thought to be fixed, unchanging, eternal lights placed on a distant sphere surrounding Earth. Even when early astronomers began to understand that Earth was not the center of everything, the idea of a stable universe persisted. The sky looked permanent, and permanence suggested peace and order. But this perception hides a deeper reality. The universe is not quiet. It is not still. It is a place of continuous motion, constant interaction, and slow but inevitable transformation on scales so large that the changes are invisible to the human eye. To understand this hidden dynamism, we must begin by realizing that everything in the universe is moving. Stars move, gas clouds move, entire galaxies move. Nothing is truly stationary. Even the seemingly fixed arrangement of stars in the night sky is only a snapshot of a moment in a long and ongoing process. Every object we see is part of a larger system shaped by gravity, and gravity never stops acting. It pulls, it bends, it gathers, and over time, it brings massive structures closer together. This is the first truth behind cosmic collisions. They are not rare accidents. They are the natural outcome of gravity acting over billions of years. Galaxies are enormous systems containing billions or even trillions of stars, along with vast clouds of gas, dust, dark matter, and planetary systems. They are not isolated islands floating independently in space. They are part of a connected cosmic environment where gravity extends across immense distances. While the space between galaxies is extremely large, it is not infinite. Over time, gravitational attraction slowly pulls galaxies toward each other. This process is incredibly slow on human timescales, but in the lifetime of the universe, it is unavoidable. When we observe distant galaxies today, we are seeing them at different stages of this long gravitational dance. At first glance, galaxies appear stable. Spiral galaxies like our own Milky Way have elegant rotating arms filled with stars, gas, and dust. These structures can exist for billions of years without obvious disruption. But this stability is not permanent in an absolute sense. It is a temporary balance between motion and gravity. Stars orbit the center of their galaxy, held in place by the combined gravitational pull of all the mass within it. Yet, galaxies themselves are not fixed in space. They drift through the universe, influenced by the gravity of nearby galaxies and larger structures. When two galaxies are far apart, their interaction is extremely weak. They may drift in the same region of space for millions or even billions of years without significant change. But as they slowly move closer, something begins to change. Gravity, even though weak over long distances, starts to accumulate its influence. It is not a sudden force. It builds gradually. The galaxies begin to feel each other more strongly, and their motions start to shift. This is the beginning of a cosmic encounter that will eventually lead to a collision. It is important to understand that when we say galaxies collide, we are not talking about solid objects crashing into each other like cars or planets. Space is mostly empty. Even within galaxies, the distances between stars are enormous compared to their sizes. So when galaxies pass through each other, direct star collisions are extremely rare. Instead, what happens is a gravitational interaction on a massive scale. Stars are pulled into new orbits. Gas clouds are compressed. Shapes are distorted. Entire galaxies are reshaped by the invisible hand of gravity. The process begins long before any visible contact occurs. As two galaxies approach each other, their outer regions start to interact first. These outer regions are made up of loosely bound stars and extended halos of gas and dark matter. These halos are not sharply defined boundaries, but diffuse regions that extend far beyond the visible parts of the galaxies. When these halos begin to overlap, the galaxies are already influencing each other significantly, even though from a distance they may still appear separate. At this stage, the gravitational forces begin to stretch and distort the shapes of the galaxies. Spiral arms may become elongated. Streams of stars can be pulled outward, forming long tails that extend into space. These tidal features are one of the first visible signs of an approaching collision. They are not violent in the explosive sense, but they represent a slow and continuous reshaping of structure. Stars that once orbited neatly within their galaxy begin to follow new paths under the influence of combined gravitational fields. As the galaxies continue to approach, these distortions become more pronounced. The original shapes of the galaxies begin to lose their symmetry. Spiral arms can become warped or disrupted entirely. Bridges of stars may form between the galaxies, connecting them through long streams of material. These bridges are not solid structures, but collections of stars and gas pulled into shared gravitational pathways. At this point, the two galaxies are no longer independent systems. They are becoming part of a single interacting structure. One of the most dramatic effects of this interaction occurs in the gas clouds within the galaxies. Unlike stars, which are relatively far apart, gas clouds can directly collide and compress. When this happens, the gas becomes dense enough to trigger rapid star formation. This process is known as a starburst. During a starburst, new stars form at rates far higher than in a stable galaxy. Entire regions of space light up with the birth of thousands or even millions of new stars. These newly formed stars are often massive and short-lived. They burn brightly and consume their fuel quickly, sometimes ending their lives in powerful supernova explosions within a few million years. This creates a cycle of intense activity within the colliding galaxies. As gas is compressed, stars form. As massive stars die, they release energy and material back into space. The galaxy becomes a dynamic environment of creation and destruction happening simultaneously. Meanwhile, at the centers of the galaxies, something even more powerful is occurring. Most large galaxies contain supermassive black holes at their cores. These black holes have masses ranging from millions to billions of times the mass of the Sunday. Under normal conditions, they are relatively quiet, slowly absorbing nearby gas and dust. But during a galactic collision, vast amounts of material can be funneled toward the center of the galaxies due to gravitational disturbances. As this material falls toward the black holes, it forms rapidly spinning disks of superheated gas known as accretion disks. These disks can become some of the brightest objects in the universe, outshining entire galaxies. In some cases, they produce powerful jets of energy that shoot outward at nearly the speed of light. These active galactic nuclei can affect regions far beyond the galaxy itself, influencing the surrounding environment on enormous scales. If both colliding galaxies contain supermassive black holes, these central objects will eventually find each other. Over time, they spiral inward due to gravitational interactions, forming a binary system. This slow dance continues until they merge into a single, even more massive black hole. This process releases enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. Although these waves are extremely difficult to detect, they carry information about some of the most powerful events in the universe. As the galaxies pass through each other, their structures become increasingly chaotic. Stars are redistributed into new orbits. Some are flung outward into intergalactic space, becoming part of long tidal streams. Others settle into new paths within the merged system. The original spiral structures are gradually destroyed. Over time, the distinct identities of the two galaxies begin to disappear. Eventually, after multiple passes through each other, the galaxies begin to merge into a single, larger system. This process can take hundreds of millions or even billions of years. The final result is often an elliptical galaxy, a more rounded and less structured system compared to the original spirals. Star formation slows down as gas is consumed or expelled. The system stabilizes into a new equilibrium, shaped by the long history of interaction. From a human perspective, this entire process is almost impossible to comprehend. It takes place over timescales far longer than human civilization, and even longer than the existence of our species. Yet, it is not rare. Galactic collisions are a fundamental part of cosmic evolution. Many galaxies we observe today show signs of past interactions, and many will experience similar events in the future. The universe, therefore, is not a static collection of isolated galaxies. It is a constantly evolving system where structures grow, interact, and transform over time. Gravity ensures that no galaxy remains completely alone forever. Over billions of years, encounters are inevitable. What we perceive as stable and unchanging is only a temporary stage in a much larger process. As we conclude this first chapter, we are left with a new understanding of the cosmos. The universe is not quiet. It is filled with motion on the largest scales imaginable. Galaxies drift, approach, and eventually collide. Stars are born in bursts of energy triggered by these encounters. Black holes grow and merge in the centers of galaxies. Entire cosmic structures are reshaped through slow but relentless gravitational interaction. What appears to be a peaceful night sky is actually a frozen moment in an ongoing cosmic story. Every galaxy we see is part of a larger journey, moving through space and time toward future encounters that will reshape its structure entirely. The silence we perceive is not absence of activity. It is simply the vast timescale of the universe unfolding beyond the limits of human perception. When galaxies begin their long journey toward one another, there is no sudden event that marks the start of the encounter. There is no explosion, no flash of light, no clear moment where motion becomes interaction. Instead, the process begins quietly, almost invisibly, across millions of years. Two galaxies that were once separated by vast distances slowly drift closer together under the influence of gravity. At first, the distance between them is so great that each galaxy remains unaffected in any noticeable way. Stars continue their orbits. Spiral arms remain intact. Gas clouds continue forming stars at their usual pace. From within either galaxy, nothing seems unusual. Yet, deep in the structure of space, the gravitational pull between them is already at work, slowly shaping their future. This early stage of interaction is dominated by something that is difficult to visualize: the extended halos of galaxies. Beyond the visible disk of stars and gas, every galaxy is surrounded by a vast halo of dark matter. This halo extends far beyond what telescopes can see, forming an invisible structure that holds the galaxy together. When two galaxies begin to approach each other, it is these halos that make the first contact. Long before stars or gas clouds interact, the dark matter halos begin to overlap and influence each other through gravity. This interaction is subtle but extremely important. It changes the trajectories of the galaxies, slightly altering their paths through space. Instead of continuing in straight or independent orbits, the galaxies begin to curve toward each other more strongly. This is not a collision yet. It is a gravitational adjustment, a slow rewriting of cosmic motion. Over time, this adjustment becomes more significant, gradually pulling the galaxies into a shared trajectory that will eventually bring them into close proximity. As the distance continues to shrink, the outermost stars of each galaxy begin to feel the gravitational influence of the other. These stars are not tightly bound to the central regions of their galaxies, so they are more easily affected by external forces. Some are pulled outward, forming elongated structures that stretch into space. Others are slightly redirected in their orbits, creating subtle distortions in the overall shape of the galaxy. These changes are still gentle, but they mark the beginning of visible transformation. At this stage, the galaxies are still far apart in absolute terms. The distance between them may be hundreds of thousands of light years, yet the process of interaction has already begun. It is important to understand that in cosmic terms, distance does not need to be small for influence to exist. Gravity operates across vast scales. Even when galaxies are separated by enormous gaps, their combined gravitational fields extend outward and begin to interact long before any physical overlap occurs. As the galaxies continue their approach, the tidal forces between them grow stronger. Tidal forces are differences in gravitational pull experienced across an object. In the case of galaxies, this means that the side facing the other galaxy experiences a stronger pull than the far side. This imbalance creates stretching effects. Stars and gas are pulled outward on one side while being less affected on the opposite side. The result is a gradual deformation of the galaxy's shape. These tidal forces create some of the most visually striking structures in the universe. Long streams of stars begin to extend from the edges of galaxies, forming what are known as tidal tails. These tails can stretch across hundreds of thousands of light years, curving gracefully through space. They are not rigid structures, but dynamic streams of matter, shaped by the combined gravitational influence of both galaxies. Some of the stars in these tails will eventually be lost to intergalactic space, while others will be pulled back into the merging system. At the same time, bridges of material can form between the galaxies. These bridges are composed of stars, gas, and dust that are stretched into long connections by gravitational forces. From a distance, it may appear as though the galaxies are reaching out toward each other, connected by luminous strands of matter. These structures are temporary, existing only during the interaction phase, but they are powerful indicators of the forces at work. Inside the galaxies, the effects of the interaction are not uniform. Different regions respond differently depending on their distance from the center and the density of surrounding material. The outer regions are more easily distorted, while the inner regions remain relatively stable for longer periods. However, even the central structures eventually begin to feel the influence of the approaching galaxy. One of the most significant consequences of this interaction is the disruption of spiral arms. Spiral galaxies, like our Milky Way, maintain their structure through a delicate balance of rotation and gravitational density waves. When another galaxy approaches, this balance is disturbed. The spiral arms can become stretched, twisted, or broken apart. In some cases, they are completely destroyed, leaving behind a more chaotic distribution of stars and gas. This disruption also affects star formation within the galaxies. As gas clouds are compressed by tidal forces, they begin to collapse more rapidly. This triggers bursts of star formation known as starbursts. These starbursts can dramatically increase the rate at which new stars are created. Entire regions of a galaxy can light up with intense stellar birth, producing clusters of young, hot, and massive stars. These newly formed stars have a profound impact on their environment. Massive stars burn through their fuel quickly and end their lives in supernova explosions. These explosions release enormous amounts of energy and distribute heavy elements into surrounding space. This enriches the galaxy with new material which can later be used to form additional generations of stars and planets. In this way, galactic collisions are not only destructive, but also creative processes that drive cosmic evolution. While the outer regions of galaxies are being stretched and reshaped, the inner regions begin to undergo their own transformation. Gas clouds that were previously stable begin to lose their balance. As they are disturbed, they funnel inward toward the galactic center. This inward flow of material feeds the supermassive black holes that exist at the cores of most large galaxies. As more material falls toward these black holes, it forms rapidly rotating accretion disks. These disks become extremely hot due to friction and gravitational compression. They emit intense radiation across the electromagnetic spectrum, sometimes outshining the entire galaxy. In some cases, this activity produces powerful jets that shoot out perpendicular to the disk at nearly the speed of light. These jets can extend far beyond the galaxy itself, influencing the surrounding intergalactic medium. If both galaxies contain central supermassive black holes, the interaction between them becomes even more complex. As the galaxies merge, these black holes gradually move toward each other due to dynamical friction, a process where gravitational interactions with surrounding matter cause them to lose energy and spiral inward. Over time, they form a binary system, orbiting each other at the center of the merging galaxy. This binary system continues to lose energy through gravitational interactions with surrounding stars and gas. Eventually, the two black holes spiral closer and closer until they merge into a single, larger black hole. This final merger releases a burst of gravitational waves, ripples in space-time that travel across the universe. Although these waves are incredibly weak by the time they reach us, they carry information about some of the most extreme events in the cosmos. As the galaxies pass through each other for the first time, the process is not a direct collision in the traditional sense. Instead, it is a gravitational interpenetration. The stars in each galaxy mostly pass by each other without direct contact due to the enormous distances between them. However, their orbits are significantly altered. Some stars are ejected into intergalactic space, while others are captured into new orbits within the combined system. This first passage often marks the beginning of a long and complex interaction. The galaxies may separate again after this initial encounter, only to be drawn back together by gravity for subsequent passes. Each pass further distorts their structure, increasing the level of mixing between stars, gas, and dark matter. Over time, the two galaxies lose their original identities and begin to form a single, shared structure. Eventually, after multiple interactions, the system settles into a new equilibrium. The final result is often an elliptical galaxy. Unlike spiral galaxies, elliptical galaxies have little internal structure. They are more rounded or elongated in shape, with stars moving in more random orbits rather than organized rotation. Star formation in these galaxies is typically much lower because most of the gas has been consumed or expelled during the collision process. From a cosmic perspective, this transformation is both an ending and a beginning. The original galaxies cease to exist as separate structures, but a new galaxy is born from their union. The stars continue to shine, the black hole continues to grow, and the system stabilizes into a new configuration. Over billions of years, this new galaxy will itself interact with others, continuing the cycle of cosmic evolution. What makes this process so profound is its scale. Entire galaxies, each containing billions of stars, are reshaped through slow gravitational interaction. The process takes place over hundreds of millions or billions of years, far beyond any human timescale. Yet, it is not an exception. It is a common feature of the universe. Many galaxies we observe today show signs of past interactions, and many more will experience similar events in the future. As we conclude this chapter, we see that galaxy collisions are not sudden crashes, but long, intricate dances shaped by gravity. They begin in silence, unfold over vast periods of time, and end in transformation. They are one of the fundamental ways in which the universe evolves, constantly reshaping itself through the slow but relentless pull of gravity across the depths of space. When we look deeper into the universe, beyond the calm appearance of galaxies drifting through space, we find that motion is not random. It is structured, guided, and deeply influenced by gravity acting across unimaginable distances. In the case of galaxy collisions, this structure becomes especially important. What appears to be two isolated galaxies approaching each other is actually a complex gravitational interaction that has been unfolding for hundreds of millions or even billions of years before any visible signs appear. By the time we notice two galaxies on a collision course, the event is already well underway in a hidden form, written into the trajectories of stars, gas clouds, and dark matter long before any visual transformation begins. One of the most striking examples of this future cosmic interaction is our own galaxy. The Milky Way is not traveling through space alone. It is part of a gravitational system that includes many nearby galaxies, but most importantly, it is moving toward a major encounter with a neighboring spiral galaxy. This approaching system is enormous, containing hundreds of billions of stars, and it is bound to our galaxy through mutual gravitational attraction. Although the distance between them is still vast in human terms, on a cosmic scale the two galaxies are already locked into a slow but irreversible path toward each other. At this stage of the interaction, both galaxies are still stable in their internal structure. The Milky Way maintains its spiral shape, with arms of stars and gas rotating around a central bulge. Star formation continues in its spiral arms, especially in regions where gas clouds are dense. The neighboring galaxy also maintains its own structure, with its own spiral arms, stellar populations, and central regions. From within either galaxy, the sky would still appear largely normal. Stars would shine as they always have. The night sky would not yet show obvious signs of the future collision. Yet, gravitational forces have already set the stage for what will eventually become one of the most dramatic events in local cosmic history. The reason this collision is inevitable lies in the nature of orbital motion within gravitational systems. Galaxies within groups do not move in simple straight lines. Instead, they follow complex trajectories shaped by the combined gravitational pull of all nearby mass. In the case of the Milky Way and its neighboring galaxy, their relative motion is not fast enough to escape each other's gravitational influence. Instead, they are bound together in a slow orbital dance that gradually brings them closer over time. Even though space itself is expanding on large scales, local gravitational systems like galaxy groups remain bound, allowing collisions to occur despite cosmic expansion. As the distance between the galaxies slowly decreases, subtle changes begin to appear in their outer regions. The halos of dark matter surrounding each galaxy begin to interact more strongly. These halos are not visible, but they contain most of the mass of each galaxy. Their gravitational influence extends far beyond the visible stars, meaning that the first signs of interaction occur long before any stars come close to each other. This interaction alters the velocity of stars in the outer regions, slightly changing their orbits and beginning the process of tidal distortion. These early distortions are not dramatic, but they are significant in shaping the future evolution of the galaxies. Stars in the outer disk of each galaxy begin to experience small shifts in their motion. Some are pulled outward slightly, while others are nudged into different orbital paths. Over time, these small changes accumulate, gradually reshaping the outer structure of the galaxies. The spiral arms remain intact for now, but they begin to show subtle signs of stretching and asymmetry. As the galaxies continue their approach, their gravitational fields begin to overlap more strongly. This leads to a region of space where the influence of both galaxies is comparable. In this region, stars and gas clouds experience competing gravitational pulls. Their orbits become increasingly complex, no longer following simple circular or elliptical paths around a single center. Instead, they begin to trace chaotic trajectories influenced by both galactic centers simultaneously. This marks a transition from stable galactic structure to dynamic interaction. One of the most visually striking consequences of this interaction is the formation of tidal tails. These are long, curved streams of stars and gas that are pulled out from the main body of a galaxy due to gravitational forces. As the galaxies draw closer, these tails become more prominent and extend farther into space. They can stretch for hundreds of thousands of light years, forming luminous arcs that connect and surround the interacting galaxies. These structures are temporary, but they represent one of the clearest signs of galactic interaction. Alongside tidal tails, bridges of material may form between the galaxies. These bridges are composed of stars and interstellar gas that have been stretched and pulled by gravitational forces. They create a visible connection between the two galaxies, giving the impression that they are reaching out toward each other. In reality, this is not a controlled process, but a natural result of gravitational interaction acting on loosely bound material in the outer regions of each galaxy. As the galaxies move closer still, the internal dynamics of each system begin to change more dramatically. The spiral arms, which were once stable structures maintained by density waves and rotation, begin to break apart. Gas clouds within the arms are compressed in some regions and stretched in others. This leads to irregular patterns of star formation. Some regions experience intense bursts of new stars, while others become less active. The overall structure of the galaxy becomes increasingly distorted. The rate of star formation can increase significantly during this stage. As gas clouds are compressed by tidal forces, they collapse more rapidly under gravity, forming large numbers of new stars in relatively short periods of cosmic time. This process creates starburst regions, where the density of young stars is much higher than in a typical stable galaxy. These young stars are often massive, hot, and short-lived, meaning they rapidly evolve and explode as supernovae, enriching the surrounding environment with heavy elements. This increase in stellar activity also has a profound effect on the energy output of the galaxy. Regions of active star formation become extremely bright, glowing intensely in ultraviolet and visible light. At the same time, supernova explosions inject energy into the surrounding gas, heating it and driving powerful shock waves through the interstellar medium. These processes make the galaxy a far more dynamic and chaotic environment than it was in its stable state. While the outer regions of the galaxies are being reshaped and star formation is increasing, the central regions are also undergoing significant changes. Each galaxy contains a supermassive black hole at its core. These black holes are relatively quiet under normal conditions, slowly accreting material from their surroundings. However, during a galactic interaction, large amounts of gas are driven toward the central regions due to gravitational torques and tidal forces. This inflow of material feeds the black holes, increasing their activity dramatically. As material falls toward the black holes, it forms accretion disks of superheated gas. These disks can reach extremely high temperatures, emitting intense radiation across the electromagnetic spectrum. In some cases, the energy output from the central region can rival or exceed the combined light of all the stars in the galaxy. This phase is known as an active galactic nucleus. It represents one of the most energetic phenomena in the universe. If both galaxies involved in the collision contain active central black holes, their interaction becomes even more complex. As the galaxies merge, the black holes gradually move toward each other under the influence of gravitational interactions with surrounding matter. This process is slow and occurs over millions of years. Eventually, the two black holes form a binary system, orbiting each other within the newly forming galaxy. This binary system continues to lose energy through interactions with nearby stars and gas. Over time, the separation between the black holes decreases, and they spiral closer together. In the final stage of this process, they merge into a single, larger black hole. This merger releases a powerful burst of gravitational waves which propagate through space-time at the speed of light. These waves carry information about the masses and motions of the merging black holes, providing a unique way to observe such extreme events. As the galaxies pass through each other for the first time, the interaction is not a direct collision in the classical sense. Instead, it is a gravitational interpenetration. Stars from both galaxies pass through each other's space without direct contact due to the vast distances between them. However, their orbits are significantly altered. Some stars are ejected into intergalactic space, becoming isolated travelers in the cosmic void. Others are captured into new orbits within the combined system. This first passage is only the beginning. After the initial encounter, the galaxies may separate again, only to be pulled back together by gravity for another pass. Each subsequent interaction increases the level of mixing between the two systems. Stars, gas, and dark matter become more intertwined, and the original structures of the galaxies become increasingly difficult to distinguish. Over time, this repeated interaction leads to the gradual formation of a single merged galaxy. The final structure is often an elliptical galaxy, lacking the distinct spiral arms of the original systems. Stars move in more random orbits, and star formation gradually declines as gas is depleted or expelled. The system settles into a new equilibrium, shaped by the long history of interaction and energy redistribution. From a cosmic perspective, this entire process is part of a larger cycle. Galaxies grow by merging with others. Structures evolve through interaction. The universe is not static, but constantly reshaping itself through gravity acting over billions of years. What we observe as separate galaxies are often only temporary configurations within this ongoing process. As we conclude this chapter, we see that galaxy collisions are not isolated events, but essential mechanisms of cosmic evolution. They shape the structure of galaxies, trigger the formation of new stars, feed supermassive black holes, and ultimately create entirely new galactic systems. They are slow, powerful, and inevitable, revealing a universe that is always in motion, always changing, and always building new structures from the remnants of old ones. As galaxies continue their slow approach toward one another, the universe enters a phase where subtle forces begin to reshape entire cosmic structures in ways that are not immediately visible but deeply transformative. What was once a simple interaction driven by distance and gravity becomes a complex interplay of gas dynamics, stellar motion, dark matter influence, and energetic feedback processes. At this stage, the galaxies are no longer just approaching objects, they are becoming connected systems, influencing each other in ways that will permanently alter their identities. One of the most important developments during this phase is the increasing role of interstellar gas. While stars are massive and visually dominant, they are actually relatively small components of a galaxy in terms of volume. The majority of the space within a galaxy is filled with extremely thin gas and dust. This material is spread out across vast distances, forming clouds that drift slowly through the galactic disk. Under normal conditions, this gas moves in relatively stable patterns, governed by the rotation of the galaxy and local gravitational conditions. But during a galactic encounter, this stability begins to break down. As two galaxies draw closer, their gas clouds begin to interact long before any direct stellar interactions occur. These clouds are sensitive to pressure, gravity, and shock waves. When the gravitational fields of two galaxies overlap, the gas begins to compress in certain regions and expand in others. This leads to the formation of dense shock fronts where gas collides, heats up, and changes its physical state. These regions become some of the most active sites of transformation in the merging system. In these compressed regions, the conditions become ideal for rapid star formation. Gas clouds collapse under their own gravity much faster than they would in a stable galaxy. This leads to the creation of massive clusters of young stars, often forming in groups rather than individually. These clusters can contain thousands or even millions of stars formed in a relatively short period of cosmic time. This process is not uniform across the galaxy. Instead, it occurs in bursts, concentrated in regions where gas density reaches critical thresholds. These bursts of star formation dramatically change the appearance of the galaxies involved. Areas that were previously dim and diffuse suddenly become bright and energetic. The combined light of newly formed stars can illuminate large regions of space, making interacting galaxies some of the most visually striking objects in the universe. These starburst regions are temporary, but they play a crucial role in the evolution of the merging system by converting large amounts of gas into stars. However, this process is not only creative, it is also destructive in a long-term sense. The most massive stars formed during these bursts live very short lives. They burn through their nuclear fuel rapidly and end their existence in powerful supernova explosions. These explosions release vast amounts of energy into the surrounding environment, heating gas, driving shock waves, and dispersing heavy elements throughout the galaxy. This feedback process can both trigger and suppress further star formation, depending on local conditions. In some regions, the energy from supernovae and stellar winds can become strong enough to push gas out of the galaxy entirely. This process is known as galactic outflow. When enough gas is expelled, it reduces the material available for future star formation. Over time, this can significantly change the evolution of the galaxy, limiting its ability to form new stars in later stages of the merger. At the same time, the structure of the galaxies themselves is undergoing dramatic transformation. The spiral arms that once defined their appearance are being stretched, twisted, and disrupted. These arms are not rigid structures, but rather patterns formed by density waves moving through the galactic disk. When external gravitational forces from another galaxy interfere with these patterns, the spiral structure begins to break down. Stars are pulled out of their organized orbits and redistributed into more chaotic trajectories. This redistribution of stars is one of the key processes in galaxy mergers. Instead of following stable circular paths around the galactic center, stars begin to move in increasingly complex orbits. Some are thrown into elongated trajectories that carry them far from their original positions. Others are pulled into new orbital configurations closer to the center of the merging system. Over time, this leads to a mixing of stellar populations that were once part of separate galaxies. The outer regions of the galaxies are particularly affected by these changes. Because the gravitational binding is weaker in these areas, stars and gas are more easily stripped away. This leads to the formation of extended tidal features, including long streams and arcs of material that extend far into intergalactic space. These structures are not static. They evolve over time, slowly dispersing or being reabsorbed into the merging system, depending on their trajectories. As the interaction continues, the gravitational influence of each galaxy becomes increasingly entangled with the other. The concept of two separate systems begins to lose meaning. Instead, what forms is a shared gravitational environment where stars from both galaxies move within a combined potential field. This marks a transition from interaction to integration, where the boundaries between the original galaxies become less and less distinct. At the centers of the galaxies, the supermassive black holes continue to play a central role in shaping the evolution of the system. As gas is driven inward by gravitational torques, it accumulates in the central regions, feeding these black holes and increasing their activity. The accretion process becomes more intense, producing high-energy radiation and sometimes launching powerful jets of material into space. These jets can influence regions far beyond the core of the galaxy, affecting gas distribution on large scales. In some cases, the energy output from the central black hole becomes so strong that it regulates the amount of gas available for star formation in the surrounding galaxy. This feedback mechanism creates a balance between growth and suppression. While gas inflows tend to increase star formation and black hole activity, energetic feedback from the black hole can heat or expel gas, limiting further growth. This delicate balance plays a crucial role in determining the final structure of the merged galaxy. As the galaxies move through multiple close encounters, their structures become increasingly distorted. The first passage typically produces the most dramatic tidal features, but subsequent interactions continue to reshape the system. Each passage redistributes energy and angular momentum among stars and gas, gradually smoothing out the differences between the original galaxies. Over time, the system becomes more symmetric, even as it loses its original spiral structure. During these repeated interactions, some stars are ejected entirely from the system. These stars become intergalactic travelers, moving through the vast empty spaces between galaxies. They no longer belong to any single galaxy and will continue their journey indefinitely unless they encounter another gravitational system. While this represents a loss of material from the merging galaxies, it also contributes to the diffuse population of stars that exists throughout galaxy groups and clusters. Eventually, the repeated gravitational interactions lead to a state of dynamical relaxation. In this state, the system has redistributed most of its energy and momentum, and the motions of stars become more stable on average, even if they remain individually complex. The merged system begins to settle into a new equilibrium configuration. This is the beginning of the final phase of the merger. The final structure that emerges from this process is often an elliptical galaxy. Unlike spiral galaxies, elliptical galaxies do not have prominent disk structures or spiral arms. Instead, they have a more rounded or elongated shape, with stars moving in a wide range of orbits. The overall motion is more random, reflecting the chaotic history of the merger process. Star formation in these galaxies is typically much lower than in spiral galaxies because much of the available gas has been consumed or expelled during earlier stages of the interaction. The transformation from spiral to elliptical galaxy is one of the most important outcomes of galactic collisions. It represents a fundamental change in structure, dynamics, and evolutionary potential. Once the merger is complete, the new galaxy will evolve more slowly, with fewer new stars being formed. Its stellar population will gradually age, and its structure will become increasingly stable over time. From a broader cosmic perspective, this process is not unusual. Many of the galaxies we observe today have undergone similar transformations in the past. The universe is filled with galaxies at different stages of this evolutionary cycle. Some are actively interacting, some are in the middle of mergers, and others are already the remnants of ancient collisions. Each galaxy carries within it the history of its past interactions, written in its structure, motion, and composition. As we reach the end of this chapter, we see that galaxy collisions are not just single events, but extended processes that reshape the universe over billions of years. They involve the interplay of gravity, gas dynamics, star formation, black hole activity, and large-scale structure evolution. They transform simple spiral systems into complex elliptical remnants. And in doing so, they continuously rebuild the architecture of the cosmos. What begins as two separate galaxies slowly drifting through space eventually becomes a single unified system forged through gravitational interaction and cosmic time. This transformation is not sudden, but gradual and inevitable. It is one of the fundamental ways in which the universe evolves, constantly reshaping itself through the quiet but relentless force of gravity acting across the vastness of space. As the process of galactic interaction continues beyond the initial encounters and tidal distortions, the universe enters a phase where the most dramatic transformations begin to unfold. The galaxies that were once distinct systems, each with their own stable structure, are now deeply entangled in a shared gravitational environment. At this stage, the concept of two separate galaxies becomes increasingly blurred. What exists instead is a vast evolving system of stars, gas, dark matter, and energy, all responding to the changing gravitational landscape created by their mutual approach. One of the most significant features of this stage is the increasing dominance of internal chaos within the galaxies. While earlier phases were characterized by relatively ordered structures being gently distorted, this stage is marked by strong disruption of that order. Stellar orbits that once followed predictable paths around a galactic center are now influenced by multiple gravitational sources. The result is a breakdown of long-established orbital patterns. Stars begin to move in more complex, less predictable trajectories, reflecting the changing shape of the gravitational potential in which they exist. This change does not happen uniformly across the system. The inner regions of galaxies, where gravitational binding is strongest, tend to retain their coherence longer. Stars closer to the central bulge remain more tightly bound and are less easily displaced. However, even these regions are not immune to the effects of the merger. Over time, repeated gravitational perturbations gradually alter their motion as well. The outer regions, by contrast, experience far more dramatic changes. Stars in these regions are often the first to be redistributed into new orbits or ejected entirely from the system. As the galaxies continue to interact, one of the most visually striking consequences is the development of long, diffuse structures composed of stars and gas. These structures, often referred to as tidal streams, extend far beyond the main bodies of the galaxies. They are formed when gravitational forces pull loosely bound material away from the galactic disks. Once formed, these streams can persist for long periods of time, slowly dispersing into intergalactic space or being reabsorbed into the merging system, depending on their trajectories and the evolving gravitational field. These tidal streams are not static. They are dynamic features that evolve as the merger progresses. Their shapes can be twisted and stretched further by continuing gravitational interactions. In some cases, they wrap around the merging galaxies in complex arcs, forming intricate patterns that trace the history of the interaction. These patterns serve as a kind of fossil record, preserving information about the past trajectories and gravitational encounters of the system. Meanwhile, within the main bodies of the galaxies, gas dynamics continue to play a crucial role. Gas clouds are highly sensitive to pressure changes, shock waves, and gravitational compression. As the galaxies merge, these effects become more pronounced. Regions of high gas density are compressed further, leading to continued bursts of star formation. At the same time, other regions may be stripped of gas entirely, reducing their ability to form new stars in the future. This uneven distribution of gas leads to a highly irregular pattern of star formation across the merging system. Some areas become extremely active, producing large numbers of young stars in relatively short periods of time. These star-forming regions can dominate the luminosity of the system, making the merger appear exceptionally bright in certain wavelengths of light. Other regions become relatively quiet, consisting mainly of older stars with little ongoing formation activity. The stars formed during these bursts are often massive and short-lived. Their rapid evolution contributes significantly to the energetic environment of the merging system. As they reach the end of their life cycles, they explode as supernovae, releasing vast amounts of energy into the surrounding gas. These explosions not only enrich the interstellar medium with heavy elements, but also generate powerful shock waves that propagate through the galaxy. These shock waves can compress nearby gas clouds, triggering additional star formation, or they can disperse gas, suppressing future star formation, depending on local conditions. This feedback loop between star formation and supernova activity creates a highly dynamic environment. It is a system in which creation and destruction occur simultaneously, each influencing the other. Over time, this feedback helps regulate the overall rate of star formation in the merging galaxies, preventing runaway collapse of gas into stars while still allowing for intense bursts of activity during key phases of the interaction. At the same time, the central regions of the galaxies continue to evolve under the influence of their supermassive black holes. As gas is funneled inward by gravitational torques, it accumulates in the central regions, forming dense, rapidly rotating accretion disks. These disks become extremely hot due to friction and compression, emitting large amounts of radiation across a wide range of wavelengths. In some cases, the energy output from these central regions can briefly outshine the combined light of the entire galaxy. This phase of intense central activity is often associated with what are known as active galactic nuclei. These regions are among the most energetic in the universe, driven by the accretion of matter onto supermassive black holes. In addition to radiation, these systems can also produce powerful jets of charged particles that are launched perpendicular to the accretion disk. These jets can extend far beyond the galaxy itself, influencing the surrounding intergalactic medium and contributing to the large-scale distribution of energy in the universe. As the merger progresses, the supermassive black holes at the centers of the galaxies begin to move closer together. This process is driven by dynamical friction, where the gravitational interaction between the black holes and surrounding stars and gas causes the black holes to lose energy and gradually spiral inward. This is a slow but persistent process that continues over millions or even hundreds of millions of years. Eventually, the two black holes form a binary system orbiting around their common center of mass. This binary system continues to interact with surrounding matter, losing energy through gravitational interactions. As they spiral closer together, their orbits become faster and tighter. In the final stages, they emit strong gravitational waves, ripples in the fabric of space-time that carry energy away from the system. These gravitational waves are extremely difficult to detect, but they represent one of the most powerful phenomena associated with galaxy mergers. When the black holes finally merge, they form a single, larger black hole. This event releases a burst of gravitational wave energy that propagates outward through the universe, carrying information about the masses and dynamics of the merging black holes. While this central process unfolds, the larger structure of the merging galaxies continues to evolve. The repeated gravitational interactions between the two systems gradually redistribute energy and angular momentum among stars and gas. Over time, this leads to a smoothing of the overall structure. The sharp features of spiral arms and distinct galactic disks become less pronounced. Instead, the system begins to take on a more diffuse and rounded appearance. During this stage, many stars are also redistributed into extended halos surrounding the merging system. These halos can become extremely large, containing stars that have been gravitationally scattered during the interaction. Some of these stars are no longer strongly bound to the main body of the galaxy, but instead move on long, extended orbits that take them far from the central regions before returning over very long timescales. The overall effect of these processes is the gradual transformation of two distinct spiral galaxies into a single, more complex system. This system is characterized by a mix of stellar populations, a reduced level of organized rotation, and a more spheroidal or elliptical overall shape. The transition is not abrupt, but continuous, reflecting the gradual nature of gravitational evolution. As gas is consumed, expelled, or converted into stars, the rate of new star formation begins to decline. The most active phase of the merger, characterized by intense starburst activity, gradually gives way to a more stable phase. In this later stage, the system becomes dominated by older stars that were formed before or during the early stages of the merger. New star formation continues, but at a much lower rate compared to the peak of the interaction. The final outcome of this long process is a galaxy that is fundamentally different from its original components. It is often larger, more massive, and more spheroidal in shape. Its internal structure is less ordered, with stars moving in a wide range of orbital directions rather than in a single rotating disk. This type of galaxy is known as an elliptical galaxy, and it represents one of the most common end states of galaxy mergers. From a cosmic perspective, this transformation is not an anomaly, but a fundamental part of galaxy evolution. Many of the galaxies we observe in the universe today are the result of past mergers. Their structures, stellar populations, and dynamics all carry the imprint of previous interactions. Even galaxies that appear relatively isolated may have experienced mergers in their past or will do so in the future. As we conclude this chapter, we see that galaxy collisions are not simple events, but extended processes that reshape the very structure of galaxies over vast periods of time. They involve the redistribution of matter, the triggering of star formation, the growth and merging of black holes, and the transformation of galactic morphology. Through these processes, the universe continually evolves, building new structures from the remnants of old ones and maintaining a dynamic balance between order and chaos on the largest scales. As the merging galaxies continue their long and complex interaction, the universe enters a stage where the most intense physical processes begin to dominate the evolution of the system. The early phases of approach and tidal distortion have already reshaped the outer structures, and the repeated gravitational encounters have transformed the orbits of countless stars. Now, the system begins to enter a phase of extreme activity, where energy, matter, and gravity interact in ways that fundamentally redefine the appearance and behavior of the galaxies involved. At this point, the gas within the merging system becomes one of the most important drivers of change. Unlike stars, which are relatively stable and evolve slowly, gas is highly responsive to external forces. It reacts quickly to compression, heating, and shock waves. As the galaxies continue to interact, vast clouds of gas are compressed in different regions of the system. These compressions do not occur evenly. Instead, they form complex networks of dense regions where conditions become ideal for rapid star formation. This is the beginning of what astronomers describe as a starburst phase. During a starburst, the rate of star formation increases dramatically compared to normal galactic conditions. Entire regions of a galaxy can become active stellar nurseries, producing thousands or even millions of new stars in a relatively short period of cosmic time. These regions are not isolated. They are often distributed across the merging system, appearing wherever gas density reaches critical levels due to gravitational compression and shock interactions. The newly formed stars in these regions are not typical low-mass stars like the Sun. Many of them are massive, hot, and extremely luminous. These massive stars consume their nuclear fuel at a rapid rate, meaning they have very short lifespans compared to smaller stars. While they shine brilliantly for a few million years, they quickly evolve and end their lives in powerful supernova explosions. This creates a cycle of rapid formation and destruction that defines the energetic environment of the merging galaxies. As these supernovae occur, they inject enormous amounts of energy into the surrounding gas. This energy heats the gas, increases its pressure, and drives shock waves through the interstellar medium. These shock waves can have two opposite effects depending on local conditions. In some regions, they compress nearby gas clouds, triggering additional star formation. In other regions, they disperse gas, preventing it from collapsing further. This creates a highly dynamic feedback loop where star formation both triggers and regulates itself through energetic feedback processes. The result is a highly irregular and chaotic pattern of star formation across the merging system. Some regions become extremely bright and active, glowing intensely due to the presence of young, massive stars. Other regions become relatively quiet, dominated by older stellar populations and depleted gas reserves. This uneven distribution of activity gives the merging galaxies a patchy and complex appearance when observed across different wavelengths of light. While star formation is accelerating in certain regions, the large-scale structure of the galaxies continues to evolve under the influence of gravitational forces. The repeated interactions between the galaxies cause significant redistribution of angular momentum. This means that the organized rotational motion that once defined the spiral structure of each galaxy is gradually being disrupted. Stars that once followed orderly circular orbits around a galactic center are now moving in more complex and randomized trajectories. This loss of organized rotation is a key factor in the transformation of spiral galaxies into more elliptical structures. In spiral galaxies, the disk structure is maintained by a balance between gravitational attraction and rotational motion. When this balance is disrupted by a major interaction, the disk becomes unstable. Stars are no longer confined to a thin rotating plane. Instead, they begin to occupy a more three-dimensional distribution of orbits, creating a thicker and more spheroidal structure. As this structural transformation progresses, the galaxies begin to lose their distinct spiral features. Spiral arms, which are maintained by density waves moving through the disk, become increasingly difficult to sustain. The gravitational disturbances caused by the interaction interfere with these waves, breaking them apart and dispersing the material that once formed them. Over time, the elegant spiral patterns fade, replaced by a more chaotic and diffuse distribution of stars. At the same time, the central regions of the galaxies become increasingly active. Gas that is disturbed in the outer regions is often funneled inward toward the galactic centers due to gravitational torques. This inflow of material feeds the supermassive black holes that reside at the cores of most large galaxies. As more gas accumulates in these central regions, the accretion rate onto the black holes increases significantly. This increased accretion leads to the formation of extremely energetic accretion disks. These disks are composed of gas that is heated to extreme temperatures as it spirals inward under the influence of gravity. The friction and compression within the disk generate intense radiation, making these central regions some of the brightest sources in the entire merging system. In some cases, the energy output from the central black hole region can temporarily exceed the combined luminosity of all the stars in the galaxy. In addition to radiation, these active central regions can also produce powerful jets of high-energy particles. These jets are launched perpendicular to the accretion disk and can travel vast distances into intergalactic space. They carry energy and momentum away from the central region, influencing the surrounding environment on scales much larger than the galaxy itself. These jets can heat surrounding gas, prevent it from collapsing into new stars, and even shape the large-scale structure of the intergalactic medium. As the galaxies continue to merge, the central black holes themselves begin to move closer together. This process is driven by dynamical friction, where the gravitational interaction between the black holes and surrounding stars and gas causes them to lose energy over time. As they lose energy, they spiral inward toward each other, gradually forming a bound binary system at the center of the merging galaxy. This binary black hole system represents one of the most extreme environments in the universe. The two black holes orbit each other at incredible speeds, while continuing to interact with surrounding matter. As they orbit, they emit gravitational waves, which carry energy away from the system. These waves are ripples in space-time itself, propagating outward at the speed of light and gradually reducing the separation between the black holes. Over time, this process causes the black holes to spiral ever closer together. The orbital period decreases, the velocity increases, and the system becomes more compact. In the final stages of this evolution, the black holes approach each other at a significant fraction of the speed of light. When they finally merge, they form a single, more massive black hole. This event releases a sudden burst of gravitational wave energy, marking the culmination of the central merger process. While these central processes unfold, the outer regions of the galaxies continue to evolve as well. Stars that were originally part of separate galaxies are now fully mixed within the combined system. Some of these stars have been ejected into extended orbits, forming diffuse halos around the merged galaxy. Others remain in more tightly bound orbits closer to the center. The overall structure of the system becomes increasingly smooth as time progresses, losing the sharp boundaries that once defined the original galaxies. In some cases, stars are completely ejected from the system due to gravitational interactions during the merger. These stars become unbound and drift through intergalactic space. They are no longer associated with any particular galaxy and will continue to travel indefinitely unless they encounter another gravitational system. While relatively rare on a per-star basis, the cumulative effect of these ejections contributes to the population of intergalactic stars that exist throughout galaxy clusters. As the merger progresses toward completion, the system begins to approach a state of dynamical equilibrium. This does not mean that all motion stops, but rather that the overall structure becomes stable on large scales. Energy and angular momentum have been redistributed throughout the system, and the chaotic interactions of the earlier phases begin to settle into a more organized configuration. The final result of this process is typically a large elliptical galaxy. This type of galaxy lacks the prominent disk and spiral structure of its progenitors. Instead, it has a more rounded or elongated shape, with stars distributed in a three-dimensional configuration. The motion of stars within this system is more random compared to the ordered rotation of spiral galaxies. This reflects the complex history of interactions that led to its formation. Star formation in the newly formed elliptical galaxy is significantly reduced compared to earlier stages. Most of the available gas has been consumed during the starburst phase, expelled by energetic feedback processes or heated to temperatures that prevent it from collapsing into new stars. As a result, the galaxy becomes dominated by older stellar populations. These stars continue to evolve, but the rate of new star formation declines significantly. From a long-term perspective, this marks a transition in the life cycle of the galaxy. It moves from a highly active, rapidly evolving system to a more stable and slowly changing one. The energetic processes of collision and merger give way to gradual evolution, dominated by stellar aging and slow gravitational relaxation. As we conclude this chapter, we see that galaxy collisions are not simply destructive events, but transformative processes that reshape the structure and evolution of galaxies. They trigger intense periods of star formation, feed supermassive black holes, redistribute stellar populations, and ultimately create entirely new galactic structures. Through these processes, the universe continually evolves, building complexity through interaction and change across unimaginable timescales. As the merger between galaxies progresses beyond its most violent and chaotic phases, the universe begins to reveal a different kind of transformation. The dramatic bursts of star formation, the tidal distortions, and the intense activity around supermassive black holes gradually start to subside. What remains is not calm in the human sense, but a slow settling of cosmic structure into a new form of balance. This stage is often misunderstood as an ending, but in reality, it is a transition into a long-term evolutionary phase where the merged system begins to define its final identity. At this point, the galaxies that once approached each other as distinct spiral structures have now become deeply interwoven. Their stars, gas, and dark matter have been redistributed into a single gravitational system. The original shapes that once defined them are no longer clearly visible. Instead, what exists is a more unified structure, still evolving but increasingly stable on large scales. The process of merging has not erased the past, but it has rearranged it into a new configuration. One of the most important changes during this stage is the reduction in available gas. Gas is the raw material for star formation, and during the earlier phases of the collision, much of it was consumed in intense starburst activity or expelled by energetic feedback from supernovae and active galactic nuclei. As a result, the merged system now contains significantly less cold, dense gas than it did at the beginning of the interaction. This has a direct impact on the rate of new star formation. With less gas available, the formation of new stars slows dramatically. The massive bursts of star creation that defined the earlier stages fade into more isolated and sporadic events. Instead of widespread stellar nurseries across the galaxy, star formation becomes limited to small pockets where residual gas still exists in sufficient density. These regions are no longer dominant features of the galaxy. They are rare and localized, often hidden within a much larger background of older stars. The stellar population of the merged galaxy begins to reflect this change. Most of the stars present are now older, having formed either before the merger or during its early and most active phases. These stars continue to evolve according to their own life cycles, but without significant new generations of stars being formed, the overall population becomes increasingly aged. This gives the galaxy a more uniform and reddish appearance when observed in optical wavelengths, since older stars tend to emit more light in the red and infrared parts of the spectrum. As star formation declines, the internal dynamics of the galaxy also begin to stabilize. During the merger, gravitational interactions cause stars to move in highly complex and often chaotic orbits. However, as the system settles, these motions gradually become more regular on large scales. While individual stellar orbits remain diverse and random, the overall distribution of motion reaches a statistical equilibrium. The galaxy no longer undergoes large-scale structural changes driven by external gravitational disturbances. Instead, its evolution becomes dominated by internal processes that occur over much longer timescales. One of the most significant remaining sources of energy in the system is the central supermassive black hole, or in some cases, the newly formed merged black hole, resulting from the coalescence of two original central black holes. This object continues to influence its environment through gravitational interaction and occasional accretion of surrounding material. However, as the supply of gas diminishes, the activity of the central black hole also begins to decline. Without a steady inflow of material, the accretion disk around the black hole becomes less active. The intense radiation that characterized earlier phases weakens over time. Jets, if present, become less powerful or cease entirely. The central region transitions from a highly energetic active state to a more quiescent one. The black hole remains an important gravitational anchor at the center of the galaxy, but its influence becomes less dramatic in terms of energy output. This reduction in central activity marks an important shift in the overall behavior of the galaxy. During the merger, the central region was a dominant source of energy and structure-shaping forces. Now, the galaxy becomes more evenly governed by the collective gravitational influence of its stars and dark matter halo. The system is no longer driven by violent central activity, but by the long-term balance of mass distribution and orbital motion. Meanwhile, the outer regions of the galaxy continue to evolve in a more subtle way. The tidal tails and streams that were formed during the merger begin to disperse. Some of this material remains loosely bound to the galaxy, slowly falling back into the main structure over long periods of time. Other parts become completely unbound, drifting into intergalactic space and contributing to the diffuse background of stars that exists between galaxies in clusters. These extended structures serve as a lingering memory of the merger process. Even billions of years after the event, faint traces of tidal streams can still be detected around galaxies. They reveal the paths of past interactions and provide evidence that the current structure of the galaxy is the result of a long and complex evolutionary history. In this way, the galaxy carries within it a record of its own formation, written in the distribution of its outermost stars. As time continues, the merged galaxy gradually becomes more spheroidal in shape. Unlike spiral galaxies, which have well-defined disks and arms, this new structure is more three-dimensional and less organized in terms of large-scale patterns. Stars move in a wide range of orbital directions, creating a system that appears more rounded or elliptical when viewed from a distance. This shape is not the result of a single event, but of the cumulative effects of gravitational interactions during the merger process. The transition to an elliptical structure represents a fundamental change in the identity of the galaxy. It is no longer defined by rotation in a thin disk, but by a more random distribution of stellar orbits. This change reflects the violent history of the merger, during which ordered motion was disrupted and redistributed throughout the system. The final structure is stable, but it is a stability born from chaos rather than long-term isolation. Inside this new galaxy, the stellar populations continue to evolve. Massive stars formed during the merger phase have already completed their life cycles, leaving behind remnants such as neutron stars and black holes. Medium and low-mass stars continue to shine for billions of years, gradually aging and changing their internal structures. Over extremely long timescales, even these stars will evolve into white dwarfs, slowly cooling remnants of once active stellar objects. As the galaxy ages, the overall brightness slowly decreases. Without significant new star formation, the most luminous and short-lived stars disappear first, leaving behind a population dominated by longer-lived, less luminous stars. The galaxy becomes dimmer in visible light, but continues to emit strongly in infrared wavelengths due to its large population of older stars. The dark matter halo of the galaxy also plays an important role in maintaining its structure during this phase. Although invisible, it provides the gravitational framework that holds the galaxy together. The distribution of dark matter remains relatively unchanged by the merger, except in how it is redistributed between the original systems. It continues to influence the motion of stars and gas, ensuring that the galaxy remains gravitationally bound even as it evolves internally. At the larger scales, the galaxy is now part of a broader cosmic environment that also includes other galaxies, groups, and clusters. While individual galaxies may have merged and transformed, the larger structure of the universe continues to evolve under the influence of gravity and cosmic expansion. The merged galaxy may eventually interact with other nearby systems, continuing the cycle of gravitational encounters over even longer timescales. However, in many cases, galaxies within a group may remain relatively isolated after major mergers. Once a large merger has occurred, the resulting galaxy often becomes the dominant gravitational object in its local environment. It may have already absorbed or disrupted most nearby smaller galaxies, leaving it as a central structure within its region of space. In this case, its future evolution becomes more gradual and less influenced by major external interactions. This long-term phase of galactic evolution is characterized by slow change rather than dramatic transformation. The galaxy continues to age, stars continue to evolve, and black holes continue to slowly accrete material from their surroundings. But the intense, violent processes of collision and merger are largely complete. What remains is a stable but evolving system, shaped by its past but moving toward a quieter future. From a broader perspective, this stage of galactic evolution highlights an important principle of the universe. Complexity often arises from interaction and disturbance, but stability emerges from the redistribution of energy and matter over time. The violent processes of collision ultimately lead to more stable structures, even if those structures are fundamentally different from what existed before. As we conclude this chapter, we see that the aftermath of galaxy collisions is not an endpoint, but a transformation into a new phase of cosmic existence. The merged galaxy carries within it the history of its formation, encoded in its structure, motion, and composition. It stands as a long-term result of gravitational interaction, star formation, black hole evolution, and cosmic redistribution of matter. And even as it settles into relative stability, the universe around it continues to evolve, ensuring that no structure remains truly permanent on the largest scales of time. As the long process of galactic merger continues to unfold, the system that once consisted of two distinct spiral galaxies has now fully transitioned into a single, unified structure. The violent interactions that defined the earlier stages have largely subsided, but their effects remain deeply embedded in the new galaxy. What now exists is not a simple continuation of either original system, but a completely transformed object shaped by gravitational evolution, gas dynamics, stellar redistribution, and the slow relaxation of cosmic structure over time. At this stage, the galaxy has entered a period where large-scale structural changes are rare, but internal evolution continues. The most dramatic transformations are now in the past. The system has already passed through phases of intense star formation, black hole activity, tidal distortion, and orbital disruption. What remains is a galaxy that appears more stable on the surface, but is still evolving in subtle and important ways beneath that stability. One of the most defining characteristics of this post-merger galaxy is its overall shape. Unlike spiral galaxies, which maintain flat, rotating disks with clearly defined arms, this new system has taken on a more three-dimensional and diffuse structure. Stars are no longer confined to a thin plane of rotation. Instead, they are distributed in a much broader range of orbits, forming a more spherical or slightly elongated shape. This transformation is the direct result of gravitational mixing during the merger process. During the collision, the ordered rotational motion of the original galaxies was disrupted. Stars were scattered into new trajectories, gas was compressed and redistributed, and angular momentum was exchanged across the entire system. As a result, the final galaxy does not retain the organized structure of a disk. Instead, it becomes what astronomers classify as an elliptical galaxy, characterized by a smooth, featureless appearance and a lack of prominent internal structure. Despite this apparent simplicity, the internal dynamics of the galaxy remain complex. Stars continue to orbit the central region, but their motions are no longer aligned in a single plane. Instead, they follow a wide variety of orbital paths, including elongated, tilted, and highly eccentric trajectories. This diversity of motion reflects the chaotic history of the merger, where gravitational interactions continually altered the paths of individual stars over millions of years. The absence of significant gas plays a major role in maintaining this structure. Most of the original gas that existed in the progenitor galaxies has been consumed during starburst phases or expelled through energetic feedback processes. Without large reservoirs of cold gas, there is little material available to form new stars or rebuild a disk structure. This means that the galaxy cannot easily return to a spiral form once it has been transformed into an elliptical system. As a result of this gas depletion, star formation rates within the galaxy are now extremely low compared to earlier stages. Only small pockets of residual gas remain, and these are often insufficient to sustain large-scale star formation. In some cases, minor interactions or internal processes may compress remaining gas clouds, leading to isolated bursts of star formation. But these events are rare and localized. The galaxy is now dominated by an aging population of stars rather than a continuously renewing stellar environment. This aging stellar population gives the galaxy a different overall appearance compared to younger, more actively star-forming systems. The light emitted is dominated by older, cooler stars which tend to radiate more strongly in red and infrared wavelengths. As a result, the galaxy appears more reddish and less blue than spiral galaxies, which contain many young, hot blue stars. This change in color is a direct indicator of the galaxy's evolutionary stage. At the center of the galaxy, the supermassive black hole continues to play a key role in shaping the surrounding environment. However, its activity has significantly decreased compared to the peak of the merger phase. Without a steady influx of large amounts of gas, the accretion disk around the black hole becomes less energetic, radiation output decreases, and any jets that were previously present weaken or disappear entirely. The black hole remains a dominant gravitational feature, but it no longer serves as a major source of energetic feedback. The relationship between the central black hole and the surrounding stellar system becomes more passive over time. While it continues to influence the orbits of nearby stars through gravity, it no longer drives large-scale changes in the galaxy's structure. Instead, it acts as a stabilizing anchor around which the inner regions of the galaxy are organized. Stars in the central region move in complex orbits, influenced by the deep gravitational potential well created by both the black hole and the surrounding dense stellar core. In the outer regions of the galaxy, remnants of the merger process can still be observed. Faint tidal streams and diffuse stellar halos extend far beyond the main body of the galaxy. These structures are composed of stars that were once part of the original spiral galaxies but were redistributed during the collision. Although these streams gradually disperse over time, they can persist for billions of years, serving as long-lasting evidence of the galaxy's merger history. These outer structures are important for understanding the past evolution of the galaxy. By studying their shapes, velocities, and chemical compositions, astronomers can reconstruct the sequence of events that led to the current configuration. In this sense, the galaxy carries within it a detailed fossil record of its own formation, preserved in the motions and distributions of its outermost stars. Within the main body of the galaxy, the stellar population continues to evolve according to well-understood physical processes. Massive stars formed during earlier starburst phases have already completed their life cycles, leaving behind compact remnants such as neutron stars and stellar black holes. Medium and low-mass stars continue to burn their nuclear fuel at slower rates, gradually evolving into later stages such as red giants, white dwarfs, and eventually cooling remnants. Over extremely long timescales, the overall luminosity of the galaxy will continue to decrease as brighter, shorter-lived stars disappear. The galaxy becomes increasingly dominated by long-lived, low-mass stars that emit relatively little energy compared to their more massive counterparts. This gradual dimming is a natural consequence of stellar evolution and the lack of new star formation to replenish the population of bright young stars. The dark matter halo surrounding the galaxy remains a crucial but invisible component of its structure. Although it does not emit light or interact electromagnetically, its gravitational influence is essential for maintaining the overall stability of the system. The distribution of dark matter helps determine the orbital behavior of stars and provides the underlying framework that holds the galaxy together on the largest scales. In the broader cosmic environment, this galaxy now exists as part of a larger network of structures, including galaxy groups and clusters. While it may have undergone a major merger in its past, it is still subject to the gravitational influence of nearby galaxies. In some cases, it may eventually interact with other systems in the future, leading to additional mergers or tidal interactions. However, these events are typically separated by vast timescales, allowing long periods of relative stability between major interactions. This cycle of interaction and stability is a fundamental feature of cosmic evolution. Galaxies grow and change through mergers, but also spend long periods in relatively isolated states where internal processes dominate their evolution. Over time, repeated cycles of interaction lead to the formation of increasingly massive and complex systems, while periods of stability allow those systems to evolve gradually and settle into new configurations. The galaxy that results from a major merger is therefore not a final endpoint, but a stage in an ongoing evolutionary sequence. It represents the accumulated history of past interactions and the foundation for future development. Its structure, composition, and dynamics all reflect the long and complex processes that shaped it over billions of years. As we conclude this chapter, we see that the aftermath of a galaxy collision is not a return to simplicity, but the emergence of a new kind of complexity. The merged galaxy is more massive, more structurally diverse, and more dynamically mixed than its progenitors. It is a system shaped by both destruction and creation, where old structures have been dismantled and new ones formed in their place. This is the nature of cosmic evolution at galactic scales. Through collisions and mergers, the universe continuously reorganizes itself, building new structures from the remnants of old ones and ensuring that even in apparent stability, change is always present beneath the surface. As the merged galaxy settles further into its long-term state, the universe enters a phase where change becomes extremely slow on the scale of human perception, yet still deeply significant on cosmic timescales. The dramatic events of the merger, the violent starbursts, the tidal disruptions, and the central black hole activity are now part of the galaxy's distant past. What remains is a system that appears stable and unified, but is still gradually evolving through internal processes that continue to shape its structure over billions of years. At this stage, the galaxy is fully recognized as a single elliptical system. Its shape is smooth, rounded, and largely featureless compared to the spiral structure it once had. There are no prominent arms, no clear disk, and no large-scale patterns of organized rotation. Instead, the stars are distributed in a broad, three-dimensional structure, moving in a wide variety of orbital paths that reflect the chaotic history of the merger that formed it. This new identity is not just a change in appearance, it represents a fundamental shift in how the galaxy evolves. Spiral galaxies are often actively forming new stars due to abundant gas in their disks, while elliptical galaxies like this one are much more passive systems. Their evolution is dominated by the slow aging of existing stars rather than the creation of new ones. This difference defines the long-term fate of the galaxy. The stellar population within the galaxy is now overwhelmingly composed of older stars. These stars were formed either before the merger or during its most active phases. As time passes, more of the massive stars that once lit up the galaxy have already completed their life cycles. They have exploded as supernovae, leaving behind neutron stars or black holes, or evolved into white dwarfs that slowly cool over time. What remains is a population dominated by longer-lived, lower-mass stars that burn their fuel slowly and steadily. This aging process has a direct impact on the overall appearance of the galaxy. The light emitted becomes increasingly dominated by red and infrared wavelengths. This is because cooler, older stars emit less high-energy blue light compared to young, hot stars. As a result, the galaxy appears more reddish when observed from a distance. This color shift is a clear indicator of its evolutionary stage and reduced star formation activity. One of the most important reasons for the decline in star formation is the depletion of cold gas. During the merger process, much of the original gas content of the progenitor galaxies was consumed in starburst events or expelled by energetic feedback from supernovae and active galactic nuclei. Without a sufficient reservoir of cold, dense gas, the galaxy can no longer sustain large-scale star formation. Any remaining gas is either too diffuse or too hot to collapse efficiently into new stars. Occasionally, small pockets of gas may still cool and condense, leading to localized regions of star formation. However, these events are rare and isolated compared to the widespread star formation that occurred during the merger phase. They do not significantly alter the overall structure or evolution of the galaxy. Instead, they represent minor fluctuations within a largely stable system. The central supermassive black hole continues to exist as a dominant gravitational feature within the galaxy. However, its role has changed significantly compared to earlier stages. During the merger, it was highly active, accreting large amounts of gas and producing intense radiation and powerful jets. Now, with limited gas available, its activity has decreased substantially. It remains massive and influential, but relatively quiet. This transition from active to quiescent state is a natural consequence of the galaxy's evolution. Without a steady supply of material falling into the central region, the accretion disk around the black hole becomes thin and less energetic. Radiation output decreases, and any jet activity becomes weak or intermittent. The black hole still shapes the motion of nearby stars through its strong gravitational field, but it no longer dominates the energy output of the galaxy. The surrounding stellar environment around the black hole has also stabilized over time. Stars in the central region move in tightly bound orbits, influenced by the deep gravitational potential well created by the black hole and the dense stellar core. These orbits are complex, often highly eccentric, and oriented in many different directions, reflecting the turbulent history of the merger. However, on large scales, the system has reached a stable configuration where stars remain bound and continue to orbit without major disruptions. In the outer regions of the galaxy, faint remnants of the merger can still be observed. These include diffuse stellar halos and long, thin streams of stars that extend far beyond the main body of the galaxy. These structures are the last visible traces of the original spiral galaxies that merged to form the current system. Over time, these streams slowly disperse into the surrounding intergalactic space, but in many cases they can persist for billions of years, gradually fading but never completely disappearing. These outer features are important for understanding the history of the galaxy. They act as a record of past interactions, preserving information about the trajectories, masses, and gravitational interactions that occurred during the merger. By studying these structures, it is possible to reconstruct the sequence of events that led to the formation of the current galaxy, even though the original structures themselves no longer exist. Within the main body of the galaxy, stellar evolution continues at a slow and steady pace. The most massive stars have already ended their lives, while medium and low-mass stars continue to evolve through their natural life cycles. Over time, more stars will leave the main sequence and become red giants, white dwarfs, neutron stars, or black holes. This ongoing evolution gradually changes the composition of the galaxy, even though its overall structure remains stable. As billions of years pass, the galaxy becomes increasingly dominated by compact stellar remnants and long-lived low-mass stars. White dwarfs slowly cool and fade, neutron stars remain as dense remnants of past supernovae, and black holes continue to exist as silent gravitational objects scattered throughout the galaxy. This population represents the final stages of stellar evolution within the system, long after the peak of star formation has ended. The dark matter halo continues to play a crucial but invisible role in maintaining the structure of the galaxy. It provides the gravitational framework that holds the galaxy together and governs the motion of stars on large scales. Although it does not interact directly with normal matter except through gravity, its influence is essential for the long-term stability of the system. The distribution of dark matter remains relatively unchanged compared to the visible components, preserving the overall gravitational structure of the galaxy. On the largest scales, the galaxy is now part of a cosmic environment that continues to evolve through the slow movement of galaxy groups and clusters. While major mergers, like the one that formed this galaxy, are relatively rare on short timescales, they are common over billions of years. The galaxy may eventually interact with other nearby systems, leading to further mergers or gravitational disturbances. However, these events are separated by vast periods of time, allowing long phases of relative stability between major transformations. This cycle of interaction and stability is a defining feature of cosmic evolution. Galaxies grow through mergers, evolve internally during stable periods, and gradually change over time as their stellar populations age and their gas reserves are depleted. Each phase contributes to the overall history of the universe, creating a dynamic and constantly evolving cosmic structure. In the case of this merged galaxy, the current phase represents a mature stage of evolution. It has already undergone major structural transformation and now exists in a relatively stable configuration. Its future evolution will be slow and gradual, dominated by internal processes rather than dramatic external interactions. Over time, it will continue to age. Its stars will continue to evolve, and its structure will remain largely unchanged on large scales. However, even in this stable state, the galaxy is not truly static. Small-scale processes continue to operate within it. Stars move in their orbits, occasionally interacting gravitationally with one another. Compact objects, such as neutron stars and black holes, may occasionally interact or merge, producing energetic events such as gravitational wave emissions. These events are rare compared to the earlier merger phase, but they represent the ongoing activity of the galaxy on smaller scales. In addition, the galaxy is still influenced by the broader expansion of the universe. On extremely large scales, galaxies within clusters and superclusters are slowly moving apart due to cosmic expansion, although local gravitational binding can counteract this effect within galaxy groups. This means that while the galaxy remains stable within its local environment, the larger cosmic web continues to evolve around it. As we reach the end of this chapter, we see that the aftermath of a galaxy merger is not a final endpoint, but a long-lived stage in the life of a cosmic structure. The merged galaxy is stable but not unchanging. It continues to evolve slowly through stellar aging, gravitational interactions, and occasional energetic events. It carries within it the history of its formation, preserved in its structure and composition, while continuing to exist as part of a larger and ever-changing universe. This stage represents the quiet continuation of cosmic evolution, where the most dramatic changes have already occurred, and what remains is the slow unfolding of time across a vast and stable but still living system. After billions of years of evolution, interaction, and transformation, the story of a galaxy collision reaches its most settled and stable phase. What began as two separate spiral galaxies moving through the vast emptiness of space has now become a single unified cosmic structure. The violent encounters, the tidal disruptions, the starburst explosions, and the central black hole activity have all played their roles in shaping this final form. Now the galaxy stands as a mature system, no longer defined by collision, but by the long-term consequences of it. At this stage, the galaxy is fully stabilized in its elliptical form. Its structure is smooth, diffuse, and extended, lacking the organized disk and spiral arms that once defined its progenitor galaxies. The stars within it are distributed in a broad three-dimensional arrangement, moving in complex but statistically balanced orbits. There is no dominant direction of rotation that defines the system as a whole. Instead, motion is randomized on large scales, a direct result of the gravitational mixing that occurred during the merger process. This final structure is not fragile. It is one of the most stable configurations a galaxy can achieve after a major merger. The system has reached a state of dynamical equilibrium, where the overall distribution of mass and energy remains relatively constant over long periods of time. Individual stars continue to move along their orbits, but the large-scale structure of the galaxy changes only slowly, governed by gradual processes rather than dramatic events. One of the most important features of this final stage is the dominance of aging stellar populations. Almost all of the gas that once fueled star formation has been exhausted, heated, or expelled. Without this gas, the galaxy is no longer able to produce large numbers of new stars. As a result, the existing stellar population continues to age without significant replenishment. The brightest and most massive stars have already disappeared long ago, leaving behind a population dominated by older, cooler stars. These older stars define the overall appearance of the galaxy. The light emitted is primarily in red and infrared wavelengths, giving the galaxy a more subdued and uniform appearance compared to younger, actively star-forming galaxies. There are no longer bright blue spiral arms or glowing star-forming regions dominating the structure. Instead, the galaxy appears smooth and diffuse, with brightness gradually decreasing toward its outer edges. The absence of new star formation has profound implications for the future evolution of the galaxy. Without the creation of new stars, the stellar population will continue to age indefinitely. Massive remnants of earlier star formation, such as neutron stars and stellar black holes, remain scattered throughout the system, but they no longer contribute to the overall luminosity in a significant way. White dwarfs, slowly cool over extremely long timescales, gradually fading into faint, nearly invisible objects. At the center of the galaxy, the supermassive black hole continues to exist as a permanent gravitational anchor. However, its level of activity has diminished significantly compared to earlier stages of the merger. Without a steady inflow of gas, the accretion disk around the black hole becomes thin and inactive. Radiation output drops to very low levels, and any previously existing jets have long since disappeared. The black hole remains massive and influential, but it is now largely silent in terms of energetic activity. Despite this reduced activity, the black hole still plays an important role in maintaining the structure of the inner galaxy. Its strong gravitational field governs the motion of nearby stars, creating tightly bound orbits in the central region. These stars move in a dense and complex gravitational environment, reflecting the long history of interactions that brought them into this configuration. Even though the region is no longer active in terms of energy output, it remains dynamically rich in terms of orbital structure. In the outer regions of the galaxy, faint remnants of the merger process continue to exist. These include diffuse halos of stars and extremely extended tidal streams that stretch far beyond the visible boundaries of the galaxy. Over time, these structures become increasingly faint and dispersed, but they never completely disappear. They represent the last visible traces of the original spiral galaxies that once existed separately before the merger. These outer features are especially important in understanding the long-term memory of galactic evolution. Even after billions of years, they preserve information about the past interactions that shape the galaxy. Their shapes, velocities, and chemical compositions allow astronomers to reconstruct the history of the merger, providing evidence of events that are otherwise invisible in the main body of the galaxy. Within the galaxy itself, stellar evolution continues on extremely long timescales. Low-mass stars continue to burn their nuclear fuel slowly, remaining stable for billions or even trillions of years. Medium-mass stars evolve into later stages, such as red giants and white dwarfs. Massive remnants from earlier generations of stars remain as neutron stars and black holes, scattered throughout the system. These objects represent the final stages of stellar evolution, long after the peak of star formation has ended. Over time, the galaxy becomes increasingly dominated by these long-lived remnants. White dwarfs slowly cool and fade, neutron stars remain as dense and stable objects, and black holes continue to exist as gravitationally dominant but invisible features. This population defines the long-term future of the galaxy, where most of the luminous activity has already ceased and only slow, gradual changes continue to occur. The dark matter halo surrounding the galaxy remains a crucial but unseen component of its structure. It continues to provide the gravitational framework that holds the galaxy together, influencing the motion of stars on large scales. Although it does not interact with normal matter except through gravity, its presence is essential for maintaining the stability of the system. The distribution of dark matter ensures that the galaxy remains gravitationally bound even as its visible components evolve over time. On the larger scales, the galaxy is part of a broader cosmic structure that includes galaxy groups, clusters, and the cosmic web. While it may have undergone a major merger in its past, it continues to exist within this larger environment. Over extremely long timescales, it may experience further interactions with nearby galaxies, but these events are rare and separated by vast periods of time. In many cases, the galaxy will remain relatively isolated within its local group, evolving primarily through internal processes rather than external disturbances. This long-term isolation allows the galaxy to enter what can be described as a quiet evolutionary phase. Without major external influences, its changes are driven primarily by internal stellar evolution and slow gravitational relaxation. The structure remains stable, but not completely static. Subtle changes continue to occur as stars move through their orbits, remnants interact gravitationally, and compact objects occasionally merge or collide. Occasional energetic events still occur within the galaxy, although they are rare compared to earlier stages. These include interactions between compact objects, such as neutron stars and black holes. When such objects merge, they produce powerful bursts of gravitational waves which carry energy away from the system. These events are extremely rare on galactic timescales, but they represent some of the most energetic processes still occurring within an otherwise quiet galaxy. Over extremely long periods of time, even these processes will gradually diminish. As stellar remnants become more widely separated and the overall density of the galaxy decreases, interactions between them become less frequent. The galaxy slowly transitions toward a state of extreme stability, where most of its internal evolution is dominated by very slow and predictable processes. From a cosmic perspective, this final stage represents one possible endpoint in the life of a galaxy. It is not an absolute end, but a long-term equilibrium state reached after billions of years of evolution. The galaxy is no longer defined by active transformation, but by the long-lasting results of past events. Its structure, composition, and dynamics are all shaped by the history of mergers, star formation, and gravitational interactions that occurred in earlier epochs. This final state also reflects a broader principle of the universe. Large-scale structures evolve through cycles of interaction and stability. Galaxies form, interact, merge, and then settle into new configurations. Over time, these cycles produce increasingly complex systems that carry within them the memory of their formation history. Even in their most stable states, galaxies are the result of long chains of cosmic events stretching across billions of years. As we reach the conclusion of this journey through cosmic collisions, we see that galaxy mergers are not isolated incidents, but fundamental processes in the evolution of the universe. They transform structure, redistribute matter, trigger star formation, feed black holes, and ultimately create new galactic forms that persist for billions of years. The final galaxy that emerges from this process is both a beginning and an end. It is the end of a violent and transformative interaction, but also the beginning of a long and quiet evolutionary phase. Within it, the history of the collision is preserved in the motions of stars, the distribution of matter, and the structure of its halo. It stands as a living record of cosmic evolution, shaped by forces that operate on scales far beyond human experience. And even as it settles into this final form, the universe around it continues to evolve. Other galaxies move through space, interactions continue to occur elsewhere, and the cosmic web slowly changes over time. Nothing in the universe is truly permanent. Even the most stable galaxies are part of a larger and ever-changing cosmic story. This is the true nature of cosmic collisions. They are not simply destructive events, but creative processes that shape the structure of the universe itself. From two separate spiral galaxies to a single elliptical remnant, the journey is one of transformation, continuity, and long-term evolution. And within that transformation lies the deeper truth of the cosmos. Everything changes, everything interacts, and everything becomes part of something larger over time.